This example is based on an example in the statics textbook. I've got it on page 128. It's example 4.7. I don't know that it's necessarily the case that it's the same with your textbook. My edition seems to be a bit older. But the idea is that you have some sort of an angle bracket right over here. The vertical height is 0.2 meters. The horizontal length is 0.4 meters. And then you have a force of 400 newtons applied over here. And the textbook puts this angle at 30 degrees. I'm going to write it as theta, because what we can do starting right now is to actually use derivatives to talk about how things can change when we're dealing with any sort of a physical system. So if we have this as a variable theta, then for example we can talk about the horizontal and vertical components of the force. So we're going to have the force split up into an x component, which is going to be 400 sine theta, and a vertical component, which is going to be 400 cosine theta. Only because we're doing this in this strange way, you have to say that the 400 sine theta goes that away and the cosine theta goes that away. I'm not really a big fan of this. My preferred method would be to take this force over here, put an xy axis right there, use the unit circle. If this is theta at the very bottom, then that means that our total angle is 270 degrees plus theta. They have to use degrees, not radians, but still all right. 270 plus theta, and then it gives you the plus minuses for your force very easily and without you having to do any figuring out of the direction in which things go. I find that having a single system works better than having something which is a little bit ad hoc. But one way or another, we can talk about how these forces will change as theta grows bigger. So the rate of change of the horizontal component as theta changes is going to be 400 cosine theta. The rate of change over here will be negative 400 sine theta. And so negative 400 sine theta down means that it is 400 sine theta up. So the rate of change of the vertical component of the force gets moving in the upper direction, right? That makes sense. If my theta is growing bigger, then the force down is getting smaller. So its rate of change is going to be positive, because from the negatives, rate of change has to be positive to move me back up. But this is easy. Let's do something a little more interesting. This section of the book deals with the moment about the point right over here, which we label O. So if we wanted to look at the moment, be very careful there. The initial instinct is to say that you have the magnitude of the moment is the magnitude of r cross f, and that's equal to the magnitude of r crossed with the magnitude of f, and then the times, and then the instinct is to say that this is sine theta. But it isn't quite sine theta, it's this angle over here. And that's not necessarily easy to calculate. You're going to need to play around with an inverse trig to figure out this angle, then add 90 degrees, and then add theta. It ends up being a bit of a mess. Something that would be easier for us is to just figure out the moment itself. The moment is equal to r crossed with f. R is pretty simple. We move 0.4 to the right, we move negative 0.2 up, and then there isn't a vertical component just yet. We cross it with 400 sine theta, and then 400 cosine theta, and then 0. Let's see, if we look at this vector, it's actually 400 sine theta going to the right, 400 cosine theta going down. That makes this a negative. And then we can walk at it from there. See, I don't like having this theta in weird directions. But when we're dealing with it, you will see that I prefer to use the vector methods whenever possible. Personally, I prefer having just a single method for both 2 and 3 dimensions, and so I don't tend to use the scalar analysis, but that's entirely up to you and your teacher, so don't take my advice as a necessary thing. Now, to find the cross product of these vectors is pretty straightforward. Use whatever method you want, and you end up with the first 2 components being very, very easy, and then you have 0.4 times negative 400 cosine theta plus 0.2 times 400 sine theta. Right, this one's going to be double negative. And so the magnitude of the moment is going to be equal to negative 160 cosine theta plus 80 sine theta. So if we wanted to find, say, the rate of change of the moment at theta is equal to 30 degrees, it will be equal to the rate of change of this is equal to 160 times sine of theta plus 80 times cosine of theta. And when we evaluate it at theta is equal to 30 degrees, we have that the derivative, the rate of change at theta equals 30 degrees is 160 times sine of 30 degrees plus 80 times cosine of 30 degrees. Don't quite need another page. Let's just go over here and write it down. Sine of 30 degrees, just in case you don't remember, you do this, you go to 30 degrees, sine is the vertical component, so it's the small one, it's a half, so it's 160 times a half plus 80 times root 3 over 2, which gives us 80 plus 40 root 3 Newton meter per something, per degree, I guess. And that's it. It's a reasonably straightforward way of looking at things. You just use everything that you already know. You've got variables, though, instead of the constants that are given in the textbook. And once you get to the proper equation, and you just need to not be afraid of it, you take the derivative the old-fashioned way and evaluate it wherever you need. And let's do another example or two of this in later videos.